So let me, without further ado, introduce the first speaker, who is Peter Mörters. Peter, together with some of his collaborators, has done beautiful work on preferential attachment models and some of its ramification, including fitness and geometry. And today he'll be speaking about geometric preferential attachment models. Please go ahead.
Thanks, Remco, and thanks for the organizers for putting up this great program and for inviting me. So this talk here is based on joint work with Emmanuel Jacob from Lyon, and what we are going to follow up on is an old idea popularized by Barabasi and Albert in about 15 years ago, and the idea is that the features that have been observed in large real networks, like power law degree distributions, robustness of the network under attack, or the small world effect, emerge if you set up a network by putting in new vertices and connecting new vertices to existing vertices, if they have a preference for for vertices that have already a large degree in the network. So this idea was very successful, and there are two reasons for the success. Well, successful in the sense of very popular with mathematicians. One thing is that you can actually prove all these things emerging from the model, and you can do this rigorously. And the reason why you can do these things is at the same time the big failure of the model, and this is the fact that locally these networks can be approximated by trees. And this enables us to do a rigorous analysis because, as probabilists, we understand branching processes and therefore trees relatively well. At the same time, of course, that's something that we don't want to be in the model. I mean, real networks have clustering, you have triangles and so on, and if your network locally looks like a tree, you precisely don't have this. So the model looks good macroscopically. Microscopically, it looks awful and cannot, and is really a bad choice. So a plausible reason for this deficiency is that we haven't taken into account individual features of the nodes in this basic model. So one of the ideas is if we take into account that nodes have individual features that, for example, could be represented by giving them a position in space, that similarity of these individual features is an additional incentive to form links. So when a new node comes in, it will not only look for another node that has a big degree, it will also take into account how far away in space this node is. So we propose a model in which we combine the spatial structure with the preferential attachment to address this. But of course, this is not a very original idea. So several other people have set up models like this, and the model we are looking at is a generalization of a model introduced and studied by Aiello, Bonato, Cooper, Janssen, and Pralat in 2009. So I'm going to explain the model now. For convenience, I set this up in continuous time. So it's a growing sequence of graphs, GT, in continuous time. Vertices are born after standard exponential waiting times, and when they're born, they're placed uniformly at random on a torus, and for the purpose of this talk, I restrict attention to one dimension, so I put them uniformly at random on the unit circle. So they have a position, and then they are connected to the nodes that are already in the system, and this is done independently for each existing node, and the probability of making a connection is given as follows. So there is a function phi, which is a model parameter. This is a decreasing function from the non-negative reals to the number 0, 1, the profile function. And in this function, we plug in time, t, the distance of the nodes, so the new one and the one that already exists, and a decreasing function f of the in degree of the existing node. So the in degree of the older node, of the node that's already in the system, is just the number of connections to younger nodes. Okay, I could also take the degree. That wouldn't change the results that I'm looking at here, but would make the analysis more complicated. So for simplicity, I only look at the number, this in degree only looks at the number of connections to younger nodes, and that's of course the relevant quantity, because this is the quantity that's increasing over time, whereas the number of connections to old nodes, the out degree is fixed once you're born and never changes. Okay, so something about this, maybe this looks like a strange choice to you, but let me emphasize that this is a natural thing. So this is actually completely general up to one thing, and this is the occurrence of the product of time and space and spatial distance here. This choice is motivated by the fact that when a vertex comes in at time t, its nearest neighbor, because the processes, okay. So I predicted that wouldn't happen, but it does. Okay, so it will be on in a second. So the nearest neighbor will be at distance 1 over t, because we just put a Poisson process with parameter t of points on the unit circle. So if we multiply the time by the distance, we keep this product, and therefore away from 0 and 1. And so this means that this is the only choice that makes that is not degenerate in the sense that we either ignore the space by letting the probability of connecting to the nearest neighbor go to 0, or we more or less just put in a complete graph in the neighborhood by connecting automatically to the nearest neighbors. So this here is to sort of keep the effects of preferential attachment and the effect of space on the same scale. Otherwise, of course, you are free to choose f and phi, these two parameters, and that's general. So the interesting thing occur when phi is integrable, and because we still have some redundancy in the choice of parameters, so we could let f multiply the argument of f with a constant, and multiply the argument of phi with a constant, and multiply f itself with the same constant. That would just cancel out. So we have freedom to normalize, and the normalization that we'll do is we let the integral of phi of the modulus of x dx we put this equal to 1. So that's a normalization choice, and under this normalization choice, the interesting regime where we'll see a scale-free network later will be when f, this is this attachment rule here. This is how strong the preferential attachment is in the model. If this has a slope gamma, so if the limit as k goes to infinity of fk over k exists, and it's a number between 0 and 1. So when gamma becomes 0, we have no preferential attachment and no scale-free network. When gamma goes to 1, it will not be a sparse network, because the expected number of edges per vertex will explode, or the expected degree will explode. So this is the regime that this sort of fixes the regime that we're interested in. And for all the results that we're interested in, what matters is not just the precise structure of f, but just this slope gamma. So that's sort of the parameter that we derive. Everyone happy with the model? Yes, Nelly.
So the nodes are more likely to connect when they're close or when they're far?
So they prefer to connect to near vertices. Okay, so there's homophily. So if you come in, I mean, if you create a new website, you make links, you both prefer to make links to the important sites like the Google page, but also to other people who are also mathematicians or something like this. That's the idea here. Okay, so what you have, if you just look at an individual vertex in the system and look at the evolution of the degrees, when at time t a new vertex is born, and you have currently in degree k, the probability that this new vertex will link to you is, well, this is phi of times distance divided by f of your degree integrated over space, because at the birth time the new vertex gets a position, and if you carry this out, so you're on a torus, you have 2 points at a distance x, where x ranges from 0 to half. Here you make a substitution of variables, you end up with this probability, and because f is asymptotically linear and time increases much faster than this, this will go to infinity. So asymptotically, the probability of connecting will be f of k, f of your in degree, divided by t, and it will not depend on the profile function. Okay, so the in degree process, the evolution of your degree will not depend on the profile function, but of course the dependence between the degree evolutions of different vertices depends very much on the profile function. But this is an interesting feature of the model, because eventually we'll see that things like the power law exponent that only depends on this degree evolution, if we're in the self-averaging case, will only depend on f and leave us free to choose this profile function phi, which determines the occurrence of long edges in the system independently. Okay, so this model has the unique feature, as far as from all the models that I know, that you can independently choose the power law exponent and the decay of the long edges. Okay, so right, so let's go through the properties of the models that we want. So first, it's a scale-free network. So if you look at the empirical degree distribution, and I mean degree, not just in degree. So if you look at all the vertices present at time t and look at the proportion of vertices that has degree k, this converges in probability, that's what the P stands for, to some number mu of k, and this k for large k decays like k to the minus 1 plus 1 over gamma plus little o of 1. So in other words, the asymptotic degree distribution is a power law with exponent tau equals 1 plus 1 over gamma, and it only depends on gamma, the slope of f, and not on the phi. So this comes from the fact that the in degree evolution can be said, the asymptotic in degree distribution can be determined explicitly and gives a value like this, and the asymptotic out degree distribution is rather complicated, but it's light-tailed and doesn't influence the power law exponent. And then, and this was the purpose of the modeling, there is clustering in the model. So if you look at the average local clustering coefficients, again, you go over all the vertices in the graph, and you look at look at all pairs of neighbors of your vertex and look at the proportion of these neighbors who are connected. This will go to a positive value, and we have a strictly positive clustering. So let me say, because the one topic of this workshop is graph limits, what the main tool for the proof of this and many other results is, many other results of a similar form is. So if you remember the setup of the model, so this axis here is time, this here is meant to represent the torus. So minus a half, you represent this as an interval, and then the points are just a standard Poisson process here in this thin and high rectangle, and then there's a rule how they connect. And when I increase time, I just make this rectangle higher by increasing this time, this height t. If I now represent this, if I change this by an affine transformation to a rectangle that has height 1 and width t, okay, if I do this, now the points should still be the same. The interesting observation is that if I use the same rule for connecting, then so what happens here is the rule phi of time times distance divided by f of n degree. Time gets multiplied with a constant, distance gets divided by the same constant, so it just doesn't change. So if I use my rule of connecting in this picture and then make the affine transformation, I get the same picture as if I make the affine transformation, then use the same rule in this picture. That's a nice thing. So that's sort of a translation at fixed time. But when time, the dynamics of the model as time goes to infinity is completely different in these two things, right? Here, if I look at this vertex, well, there are new vertices coming in. They will connect to this. The degree will go to infinity of this fixed vertex here. In this picture, if I look at the fixed vertex, as time goes to infinity, I'm making this wider. The new vertices that come in are far away, and it turns out that after a while they stop connecting because I'm discouraging long edges, and this picture will stabilize. So in this picture, I can take a limit, and I have an infinite picture which is based on the Poisson process in the real line multiplied with the interval 0, 1. And I can set up this model on this picture here, and if I've set up the whole thing in such a way that this torus here is represented by an interval with a point centered here on this line, this point here will stay here in the middle of this picture as well as t goes to infinity, and what we see here is the Benjamini-Schramm limit of this vertex model. So it will describe a local neighborhood of a randomly chosen point in this model can be described by this infinite limit model. So the limit model is very useful to us. It's not easy to study, but it's it's not a tree or something like this, but it's very useful because it's based on Poisson process, and it has the property that if you look in a box and you have a reasonably local functional that you're interested in, if you are in a box that is sufficiently, well, there exists a random distance that after this distance what happens there is not relevant for your features anymore, and that allows us to use a law of large numbers like in Yukich and Penrose to prove these results and quite a number of similar results on, say, empirical edge length distributions and all these kind of things. So that's an encouraging thing that allows you to actually study certain statistics of this model. Okay, so but the question we're asking in this talk is whether this model still has the features that we know and like from the non-spatial preferential attachment model, like small world feature or robustness under attack. Okay, so for the robustness question, I'm going to specialize a little bit. My profile function will now be regularly varying, so I'm assuming that phi of x goes like x to the minus delta. There could be a logarithmic correction, which I'm not going to write here. So I reduce these parameters f and phi, the attachment rule and the profile function, to just these parameters delta, which is bigger than 1, and gamma, which is between 0 and 1, and delta measures the decay of the probability of long edges, and gamma the strength of the preferential attachment. Here you can see a picture of this graph. So this is just sort of the middle third of or a segment of a third of the length of the unit circle, and in this axis you see time. And these two networks have the same parameter gamma, actually the same f. So they have the same edge density, and they have the same power law exponent, 1 plus 1 over gamma here. But what they have different deltas, so different lengths, different decay of long edges. So although, I mean, the same number of edges, this looks like it has a lot more ink, but this is because the edges are longer, not because there are more edges. Okay? And so what I would like to convey is that you should think of this parameter delta also as measuring the clustering, because the network here, which has more short edges, looks much more clustered than the one which has more long edges. So the long edges are, most of them are pretty parallel here at the bottom, connect vertices of old vertices, because bottom means old. Okay, right. So the question that I'm going to study here is robustness, and the way I set this up is I call theta the proportion of vertices, or actually no, I divided it by time. So it's an asymptotic proportion of vertices in the largest connected component of our network, and I say that the network has a giant component if this proportion is positive. Then I do Bernoulli percolation. So I fix a graph GT. I run Bernoulli percolation with retention parameter P on the vertices of GT, and the network is robust if no matter what the proportion of vertices is that I delete, I still have a giant component. Okay? So by removing vertices, I cannot destroy the existence of a giant component, of course, unless I remove all of them. And it's called non-robust if there is no giant component for some p. Or in other words, robustness means that the critical percolation parameter is 0. Non-robustness means positive critical percolation parameter. And from the world of non-spatial scale-free networks, we expect the transition between robust and non-robust behavior to happen when tau passes the value 3. But it turns out this is not the case here. So here is the main theorem. If you look at the network GT, we can prove robustness if tau is less than 2 plus 1 over delta. Remember that delta is bigger than 1. This was because this should be integrable, and I've assumed that delta is bigger than 1. So this is stricter criterion for robustness, 2 plus 1 over delta. And I can prove non-robustness if tau is bigger than 3. This is to be expected because the spatial structure will not help robustness. But it's also non-robust if tau is bigger than 2 plus 1 over delta minus 1. So, and this means that the transition between robustness and non-robustness does not happen at the value 3, but at a smaller value depending on this clustering parameter. So in the picture that you've already seen, this network here is robust. This one isn't. Robustness and clustering work against each other. Okay, and so this is the phase diagram as far as we've established it. So there is clearly non-robustness if gamma is less than half. So tau bigger than 3, this means. This here is the dark blue is the phase where we've shown robustness, and this here is this whole thing is the phase where we have shown non-robustness, and there is some white area where we don't know, but what we conjecture that the blue area, this dark blue area, is actually sharp, that the criterion that's given in the top one, the criterion for robustness, is the one that actually is the rigorous one. Let me briefly say something about the proof here, because I have 5 minutes or so. So for the robustness, so what do you do? So first of all, you try to use your limit model and show that existence of a giant component is equivalent to the existence of an infinite component in this one. This is non-trivial because we have long edges and a lot of long edges in there, but it's technical but doable. Once we are in the infinite picture, we show robustness by following the strategy that in the non-spatial case produced robustness. This is, we start with a relatively old vertex and we show that we can get to an even older vertex in 2 steps. And 2 steps is because the old vertex will have a lot of young, will be collected to a lot of young vertices, and one of these young vertices hopefully is connected to an even older one. So this is how you proceed, and in the non-spatial case, if tau is less than 3, you can show that you can construct an arbitrarily long sequence of edges this way. It's harder in this case because there is space and yeah, sorry, that's somewhat more frequent than I expected. Okay, so there is space, and of course the even older vertex that you want to connect to is at some distance away in space, and therefore your edges that connect the vertex via young ones also have to be sufficiently long to reach this. And therefore you need to have a supply of long edges, and therefore this parameter delta comes in as well. So the first criterion tells you that the usual strategy works precisely under this condition, and the reason why the non-robust criterion is not so sharp is because, of course, there is the possibility that another strategy might work. Now, nobody believes this, so, well, I think nobody believes this, so I would strongly believe that this is the sharp one, but you have to prove it. And for most cases, this non-robustness proof is the easy direction because it's essentially a first moment estimate. Right? You have to estimate that when you start in some vertex, the expected number of paths of length n decays like a constant to the n, and then if you run percolation with a parameter that's less than 1 over this constant, then Borel-Cantelli gives you that you don't have an infinite component. And the difficulty here is that we have no way to calculate the probability of a chain of edges, because there is strong positive correlation between the existence of edges. In particular, if the end vertices of the 2 edges are near in space, then other points that are also near will influence the in-degree of these vertices, and therefore that will make both edges much more likely. Okay, and this positive correlation makes everything very geometric and difficult, so we're in a similar situation than Vincent Tassion in the other percolation-based talk. We would like to use we can't use the BK inequality because of this positive correlation. It doesn't hold. But eventually, the trick will be that if we take a potential long chain of edges, we will replace the edges by other edges, and on these other edges, we will eventually be able to use the BK inequality. So the trick will be to construct special paths that don't necessarily have to be in the percolated network. They just have to have a proportion of their vertices in the percolated network on which we can apply the BK inequality. So the BK inequality is a crucial tool here, and the main innovation is to put us in the situation where you can apply it. Okay, so brief comments on, yes, I'm on the way out. So brief comments, so I already said this, but another comments, there are other models by Dyson et al. That's the scale-free percolation model, and the hyperbolic random graphs, which also combine geometry and scale-free methods. In all these cases, the phase transition occurs at tau equals 3. And here it occurs at a strictly smaller value. We believe that the similar phase transition at the same place occurs when we look at typical distance. So at this, we conjecture that at the position 2 plus 1 over delta, there's a transition between log-log scaling of the typical distance in the giant component and log scaling. Okay, so I've already explained the proof techniques. So summing up, we look at in the spatial preferential attachment networks, individual features come in, and as a result, we keep the scale-free nature of the network, but get clustering. You need, for robustness, you need both strong preferential attachment and weak clustering. The phase transition, therefore, moves from tau equals 3 to a smaller value, which is a new phenomenon, and there are lots of open problems on this model. For example, we haven't identified the precise location of this phase transition. Thank you very much.
Thank you very much for this very clear talk. Are there any questions?
So your notion of robustness was randomization of edges or vertices?
Yes, you could do both edges or vertices, it doesn't matter.
A stronger notion of like adversarial attack on the network. Can you say something about that?
Yeah, I mean, if you make a targeted attack on the network in the sense that you remove the hubs, the old vertices, then of course you don't expect robustness. And because the whole thing is more fragile in this case, I expect that the results that hold for of vulnerability will translate to the spatial setup, because it's intrinsically more vulnerable. That would be my guess.
So your geometric structure here is one-dimensional. I guess you have thought about the possibility of doing this in high-dimensional, more general spaces. So.
Yeah. So in the paper we do it for d-dimensional tori, and everything goes through except the last step where we show the non-robustness, that the non-robustness goes for tau that are smaller than 3. That is based on an idea which relies on one-dimensionality, because it's sort of, we have to eliminate short edges, show that a path has a lot of long edges, and that relies on the fact that the boundary of a ball is not growing with volume, and that's a purely one-dimensional effect. I expect this also to work in higher dimensions, but you need an idea to actually do calculations in this setup.
One final question, David?
Continuing that, an old idea of mine that never caught on was a very similar model, but sort of in the near field model of distance, which is basically continuous T-shaped space, and basically, I went through the same program as you did, in that you get a 2-parameter model and you can fit any degree exponent in any clustering coefficient and do calculations. So I never thought about robustness.
Yeah.
So there's a project for a student to think about robustness there.
Thank you.
Okay, let's thank Peter once more.